In this video, we're going to be determining the stresses at release at midspan using the Force-in-the-Tendon approach for the section shown below. It's a rectangular section. You can see the dimensions 12 by 24. We have our release concrete strength 5 KSI, our area of our pre-stressing, the stiffness of our strands, and the self-weight of the section. The first thing that we'll do is we need to find our material properties. So we can take our 57,000 times the square root of 5,000 PSI divided by 1,000 pounds per kip will give us 4,030 KSI. We can find our modular ratio by taking our strand stiffness divided by our concrete stiffness, which will give us a modular ratio of 7.1. Next, we need to find all of our gross section properties because they're not given in this example. So our gross area, it's a rectangle base times height, 288 square inches. Our centroid of the section is just going to be the mid height, so 0.5 times our height, 12 inches. Our gross moment of inertia is BH cubed over 12. So that's given there, 13,824 inches to the fourth. And then the centroid, or the eccentricity of our strands is the distance between the centroid and the strands there. So D minus Y top, 20 minus 12 gives us our 8 inches. We will use both our net and transform section properties, so we need to find both. And we can start by finding our net section properties. These section properties it's our concrete section minus the area of our pre-stressing. So our net area is just our gross area, 288 square inches, minus the area of our pre-stressing, 0.459 square inches. So this will give us 287.5 square inches. Our Y top net is going to be equal to our gross area times the distance between the top and the centroid of our gross section minus our strand area and the distance between the top and the centroid of our strands. We're going to divide this by our net area, and we'll get a distance 11.99 inches. So we're taking out the area of our pre-stressing, so our centroid shifts up a little bit. Next, we can find our I net. And this is just going to be our gross moment of inertia, 13,824, plus our gross area, A, times our D squared component, 11.99 minus 12. And then we're subtracting out our AD squared component for our pre-stressing, so minus 0.459 square inches times 11.99 minus 20 squared. So this will give us an I net transformed of 13,795 inches to the fourth. So you can see it's just about equal to our gross moment of inertia, so it doesn't affect things too much. And then finally, we can find our eccentricity with our net section. So this is going to be 20 inches minus 11.99 inches, which will be 8.01 inches. So these are our short-term net section properties. Note that I have this short-term in here because if we do have non-pre-stressed reinforcement, we need to transform that non-pre-stressed reinforcement into an equivalent concrete area. So if we're doing short-term or long-term, we need to use the appropriate moment of or modulus of elasticity for our concrete. So that's why I differentiate short term there. We're also going to find our stresses using our transformed sections. So we need to find our transformed area, our transformed centroid, and our transformed moment of inertia. So starting with the transformed area, our transformed short-term at release is going to be our gross area plus our n-1, so 7.07 minus 1 times the area of our pre-stressing, 0.459. And this will give us a transformed area of 290.8 inches squared. Our Y top transformed short-term at release is going to be our gross area here, 288, times the distance from the top to the centroid of our gross section, plus our transformed steel here, so 7.07 minus 1 times 0.459 square inches, times the distance between the top and the centroid of the strands, which is just dp, 20 inches. And then we divide all this by our transformed area, 290.8 square inches. And this will give us a distance of 12.08 inches. So you can see that our transformed area of our pre-stressing is pulling our centroid down a little bit. So conceptually, our calculation here checks. The last one that we can find is we can find our transform moment of inertia. So we have our I gross plus our A d squared component for our gross area plus our A d squared component for our transformed pre-stressing. And that'll give us a transform moment of inertia of 14,001 inches to the fourth. And then finally, our eccentricity of our strands, considering our transform section, d minus the distance from the top to the centroid of our transform section, and that's given here. To find our stresses at release, we're going to need to find our pre-stress losses due to elastic shortening. And we're going to use the PCI Design Handbook approach from the 7th edition to calculate our elastic shortening losses. The first thing that we need to do is calculate our force in our strands at jacking, and this is before transfer happens. So this is our stress before transfer, 202.5 KSI times the area of our pre-stressing to give us a total force of 92.9 kips. Next, we can use the equation here for the stress in the concrete at the level of the pre-stressing given by PCI. And plugging in all of our known values, we'll get FCIR equal to 0.9 times 92.9 kips divided by 288. We're going to use our gross section properties here, plus our 92.9 force in the pre-stressing times our eccentricity squared divided by our gross moment of inertia, 13,824 inches to the fourth. And then we'll close our bracket there, and then minus our self-weight moment, which was given here as 636 kip inches times 8 inches divided by our gross moment of inertia, 13,824, will give us a stress here of 0.309 KSI. We can use this times our modulus of pre-stressing divided by our release, or our concrete modulus at release. So 28,500 divided by 4,030 times the stress that we just found, 0.309 KSI, will give us an elastic shortening loss of 2.19 KSI. Our stress after release then is just our stress before release minus our elastic shortening loss, which will give us a stress after release F sub pi of 200.3 KSI. And then to find our force, we take that stress 200.3 times the area 0.459 to give us a force here of 91.9 kips. So this is the force that we're going to use when we're calculating our stresses with our gross section and our net section. When we calculate our stresses with our transform section, we're going to use the stress or the force in the tendons before our elastic shortening loss. We're now ready to calculate our stresses using our different section properties, and we'll start with our gross section. With our gross section, we'll use the stress in the strands after elastic shortening loss, and we'll combine all of our axial stresses, our P over A stresses from our pre-stressing, with all of our flexural stresses from our pre-stressing and any applied loads. So starting with the stress in our concrete at the top fiber, with negative being compression, we'll have negative 91.9 kips divided by 288 square inches plus 91.9 times 8 inches times 12 divided by 13,824, and then minus 636 kip inches, our self-weight moment, times 12 inches, the distance from the centroid to the top, divided by our modulus of our moment of inertia, 13,824 inches to the fourth. So this will give us a stress here in the top fiber equal to negative 0.233 KSI. We can do the same thing with our bottom fiber. So we're still causing, or the strands are still causing compression in the bottom fiber, so we still have a negative 91.9 kips divided by 288. The strands are now the eccentricity of the strands is causing compression in the bottom fiber, so we'll have a minus sign there. 91.9 times 8 times 12 inches is still the distance from the centroid to the bottom for our gross section, divided by 13,824 inches to the fourth. And now our moment is going to cause tension in the bottom, so we have a positive sign there. So we'll have 636 kip inches times 12 inches divided by 13,824 inches to the fourth, which will give us a bottom fiber stress here equal to negative 0.405 KSI. So this is our top and bottom fiber stress due to our pre-stressing and our self-weight at release. We can next calculate our stresses using our net sections. So with our net section, we're supposed to use our net sections to resist any self-equilibrating forces. So this is our pre-stressing and our self-weight moment. So you can see we're going to use our net sections in place of the gross sections for all of our stress calculations. And we have the same signs and same components as we did for gross, but we can find then our top fiber stress to be negative 0.232 KSI and our bottom fiber stress to be equal to negative 0.407 KSI. Note that in this case, we have a different distance between the centroid and the top fiber and the centroid and the bottom fiber. So we just need to make sure that we use the correct distances for our two different formulas. We can do the same thing with our transform section. And here, just note that when we're using our transform section, we need to use the force in the strand and the stress in the strand before elastic shortening losses. So here we're using the strand stress before transfer, F sub PBT of 202.5. So wherever we had our strand force before, or our strand force, we need to make sure we're using the right force there. And again, we had the same equation, same components. We need to make sure that we use the correct distance, so the distance between the centroid and the top, and the distance between the centroid and the bottom of the section. And we'll get a stress then in the top of negative 0.233 KSI, and a stress in the bottom of negative 0.405 KSI. On this slide, we have a comparison between the three different methods. First, we see the compression limit and the tension limit from ACI 318 at midspan. So our compression at midspan at release. Our compression limit is going to be 0.6 times the release strength, 2.1 KSI, and our tension limit is going to be 3 times the square root of our release strength of the concrete, which will end up being 0.212 KSI. You can see in this example, or the example from the previous slides, we had a pre-stressing ratio of about 0.002, and you can see how our stresses compare. They're very similar between the three approaches, so essentially using gross sections is okay. We can see that as we increase our reinforcement ratio, the difference between the three approaches does increase, but it's still relatively minor. And that concludes this example.